We on Earth are exceptionally lucky. While we are very rarely conscious of it, we exist and are alive today because Earth has an oxygen-rich atmosphere that we are breathing right now. And not only that, but the atmosphere provides safety from the cruel environment of space. It's visually beautiful, and it gives us a place to grow, play, and develop. I'm McColgan, and you're watching Astrum, and today I will unravel the different layers of Earth's atmosphere and explain how they are so important to our existence. Let me start by showing you some of these remarkable videos. If I were to ask you where Earth's atmosphere is, I think most people would quite confidently say it was all in this area here. Surprisingly, this is not actually the case. This video was taken on the ISS, or the International Space Station, which orbits the Earth at a distance of 340 kilometers. Earth's exosphere, which depending on who you talk to is the final frontier of Earth's atmosphere, starts at roughly 500 kilometers and extends up to halfway to the Moon. The layers you are looking at in this video are in fact only the troposphere, stratosphere and mesosphere. Beyond the mesosphere, but only barely visible, are the thermosphere and then the exosphere. But what is the difference between all these spheres? What do they actually do? Let's start right at the base layer, and the layer we are most familiar with because we live in it, the troposphere. At only 20 kilometers high at the equator, it's the thinnest of all the atmospheric layers. However, the troposphere is not a consistent height across the globe. The further towards the poles you go, the lower it reaches. At the mid-latitudes of the planet, it rises to 17 kilometers, and by the poles it's only 7 kilometers high during winter. Most commercial airlines in fact try to fly above the troposphere where possible, as they can avoid most weather disturbances in the stratosphere, but we'll get to that point later. The defining thing about the troposphere is that the higher you go, the colder it gets. And from my own personal experience of living in Switzerland, this can especially be seen when it's 20 degrees centigrade at the base of a mountain, but at the top it's still snow-capped. This disparity in temperatures is due to the way heat energy is transferred with conduction, convection, and radiation. Let's understand how this works. Firstly, heat is emitted from the sun in all forms of electromagnetic radiation. Most notable to us is light. This includes not just visible light, but infrared light and ultraviolet. Light is a simple energy, and this energy turns to heat when it impacts particles. Dark, non-glossy materials absorb this energy the best, which is why asphalt on a sunny day can reach temperatures of over 65 degrees centigrade. On the other hand, Earth's atmosphere is not as good at absorbing this energy, and most of the light passes straight through. But interestingly, the atmosphere does interact with some wavelengths of light, particularly blue wavelengths. This is a process called Rayleigh scattering. Gas molecules are smaller than a wave of light, so when a light wave hits one, it can only absorb some of it. All the different colors can be absorbed, but the higher frequency blue light is absorbed more often. After a while, the gas molecule radiates the same light it absorbed in a different direction. So when you're looking at the sky, what you're seeing is the blue from sunlight being scattered by a gas particle exactly in your direction. This is why the sky appears blue. Due to the atmosphere's poor absorption of solar energy, the atmosphere is not heated very much by the sun itself, but rather through the two other processes of heat transfer, conduction and convection. Solids are much more densely packed than gases, and so are much better at absorbing the sun's light. Because of this, the ground is warmed easily by the sun. Light colors and glossy materials are not good at absorbing light and will often reflect it back. Snow, for instance, does this. Dark, matte materials absorb a lot more of this solar energy and then release the heat back into the atmosphere through conduction. Conduction is the process of a particle being heated and then releasing this energy by exciting the particles next to it. An easy way to imagine this is a pot of water on a stove. The hot pot conducts the heat to the water particles around the edge of the pot, which then heat the water particles next to them, and so on. This process of conduction is why cities are often hotter than rural locations. My capital city of London is often a few degrees warmer than the UK average on a consistent basis because the tarmac and concrete from the streets and buildings absorb and then release the sun's heat easily into the nearby atmospheric gas particles. But this happens to some degree or another across the whole world. A surface absorbs the heat of the sun and then releases it through conduction into the surface atmosphere. When gas particles are heated, they move further apart from one another, expanding and increasing in volume. This is where convection comes into play. Because the volume of the gas is increasing, but the amount of particles stay the same, its density decreases, and so the gas rises. As it rises, air pressure decreases, and the gas particles spread out even further. Individual particles begin to lose their heat energy through radiation. Eventually, the surrounding temperature is equal to the gas particle itself, and it can no longer rise. Instead, the particles start dispersing sideways. As the heat is further expended, the gas becomes cooler and denser and starts to sink again. This process happens on a grand scale near the equator and explains why the troposphere is higher near there. The equator is exposed to the most sunlight, and so when the air is heated near the surface, it rises very high. Following the process of convection, it reaches the point of no longer being hotter than the surrounding air, moves sideways, cools, and then drops again. Once at the surface, it fills the gap created by more rising air near the equator, creating this circle. This is called the Hadley cell, and similar cells can be found around the mid-latitudes and the polar regions, just to smaller extents. Because of these cells, gases from the stratosphere and the troposphere do not often mix. These cells are also the cause of trade winds, tropical rain belts and hurricanes, subtropical deserts, and the jet streams. Interestingly, because the cooled air is descending around the 30-degree latitudes, and at this point has lost much of its heavier and denser humidity, precipitation will be much less common in these parts of the world where the dry air descends. Looking at an average rainfall throughout the year, it becomes very apparent that the Hadley cells have a big impact on the weather of this planet. 75% of the total atmospheric mass of Earth can be found in the troposphere. Its composition is mostly uniform throughout the planet, being a mix of 78% nitrogen, 20% oxygen, and small amounts of other gases. The exception to this uniformity is unsurprisingly water vapor, which is affected by the water cycle. We notice the presence of water vapor in two ways: humidity and clouds. In the form of humidity, we can't see the water vapor, but can rather feel it. Water vapor we can see comes in the form of clouds. In the atmosphere, there are very small particles of dust and salt, known as aerosols. They are much larger than water vapor particles and provide a surface for the water vapor to condense onto when the vapor rises and cools. When enough water vapor particles condense onto the aerosol, a cloud droplet is formed. These droplets are so small that 1 meter squared can contain 100 million of them. When there are enough droplets, a cloud becomes visible. As the cloud becomes saturated with cloud droplets, they can merge and eventually fall from the sky in the form of a raindrop. There are many different types of clouds, and they are formed in slightly different ways, but this basic explanation will suffice for this video. As I mentioned, temperature in the troposphere decreases with height at a rate of about 6.5 degrees centigrade every 1 kilometer. Also decreasing in height is air pressure. Dividing the troposphere from the next atmospheric layer, the stratosphere, is something called the tropopause, defined as the point air temperature stops decreasing the higher you go. In fact, just above the tropopause and going into the stratosphere, it starts to get hotter again. This is because of a layer in the stratosphere that is better at absorbing solar radiation, thus warming the stratosphere, and that is the ozone layer. Ozone is 3 oxygen atoms combined into one molecule, or O3. Down in the troposphere, the oxygen we breathe is actually dioxygen, or O2. It is very beneficial in the stratosphere, as it absorbs a lot of dangerous UV light before it reaches us on the ground. The concentration of ozone in the ozone layer is actually only about 10 parts in a million, but that is enough to protect us. Ozone is formed by UV light splitting a normal O2 molecule into two oxygen atoms. One of these atoms then combines with some unbroken O2 to form O3. UV light then breaks up the O3 molecule back into O2 and an oxygen atom, and this cycle continues constantly. The stratosphere contains 20% of the mass of the atmosphere. It's called the stratosphere because it is stratified in temperature, with warmer layers higher and cooler layers closer to the Earth, the ozone increasing the temperature the higher you go. At the equator, the stratosphere starts at 20 kilometers and ends at 50 kilometers. There's not much in the way of convection in the stratosphere, the only temporary exceptions being caused by huge storms or volcanic eruption pillars. When air moves in the stratosphere, it is more often horizontally than vertically. This is why commercial airliners prefer to fly in the stratosphere where possible. There are rarely any clouds or weather, and the air isn't moving about as much. Interestingly, you may have heard of the world record skydiving jump performed by Felix Baumgartner. He jumped from the height of roughly 39 kilometers, which is still well within the limits of the stratosphere. Clouds very rarely form in the stratosphere as the air is so dry. Very occasionally, however, around the poles, nacreous clouds can form. Sometimes nacreous clouds are made of water, but rather other substances such as nitric acid. When seen just before dawn or dusk, these clouds are beautiful as they glow brightly with vivid iridescent colors. Because of the curvature of the Earth, the sun shines on them from below to provide this effect. After the stratosphere is the middle atmospheric layer, the mesosphere. Between these two layers is the stratopause, the region where the air temperature stops increasing and starts decreasing again. At this point, the air pressure is only 1,000th of what you would find on the surface. The mesosphere starts at 50 kilometers and ends at roughly 100 kilometers. Towards the top of this layer can be found the coldest places on Earth, where the temperature can drop as low as minus 143 degrees centigrade. Again, there can be a very rare type of cloud found in the mesosphere. These are called Noctilucent clouds, and they are again very beautiful. Found between 50 degrees and 70 degrees north and south of the equator, and around 76 to 85 kilometers up, they are the highest type of cloud found on Earth. Like the stratosphere's nacreous clouds, they can only be seen while the sun is below the horizon. They are a type of water ice cloud, the difference being they can form with or without collecting on dust particles and are sometimes purely water vapor clouds. The source of the water and dust this high in the atmosphere are not known with certainty, but could come from micrometeors or volcanic eruptions. Water vapor from rockets can also cause Noctilucent clouds, most recently from the SpaceX rocket Falcon 9. They are really spectacular, especially when you consider how high they are. This is a view from the perspective of the International Space Station. Even in this image, you can visibly see the different atmospheric layers, the troposphere, stratosphere, and mesosphere. Interestingly, the mesosphere is the least understood of all the atmospheric layers, even referred to as the ignorosphere, as it's above the flight capabilities of aircraft and below the minimum safe orbit of satellites due to atmospheric drag. The only times measurements can be taken are by rockets, and only for a few minutes as they ascend to the thermosphere, the next atmospheric level. As you might have guessed by now, above the mesosphere at roughly 100 kilometers is the mesopause. And as you might have guessed again, the mesopause is the point where the temperature stops decreasing and starts increasing again throughout the thermosphere. In fact, temperature can get extremely hot in the thermosphere depending on the solar activity, as much as 2,000 degrees. Although it's so hot here, because of the exceptionally low air pressure at this point, there are not enough gas particles to transfer much heat, so it would still feel well below 0 degrees. To give you an idea of how little gas there is here, above 160 kilometers, molecular interactions are so low that sound cannot travel anymore. The thermosphere is the thickest of all the atmospheric layers, rising from 100 kilometers all the way to 600 kilometers, but it only contains 0.002% of Earth's atmospheric mass. The thermosphere is actually considered by a lot of people to be the start of space. Satellites, and even the International Space Station, orbit within the thermosphere. But that's also why many satellites' orbits degrade, eventually with them burning up in the lower parts of Earth's atmosphere, because they were never really in true space, and atmospheric drag was still slowing them down enough that they eventually fell out of orbit. The thermosphere also serves an important purpose to us on Earth. A lot of the most dangerous and highest energy electromagnetic waves from the Sun are absorbed in the thermosphere, and the effects of this can be seen as beautiful aurora in the sky. These high energy waves interact with particles high in the thermosphere, exciting them and making them glow in many different colors, the most common on Earth being green. Above the thermosphere is the thermopause, which can range in height from 500 kilometers to 1,000 kilometers, depending on the time of day, the amount of solar activity, and a host of other factors. Above the thermopause is the last atmospheric layer, the exosphere. In the exosphere, there are very light gas particles like hydrogen present. However, due to the distance between these particles, they don't act as a gas, as they do not collide with other gas particles. They are, however, still gravitationally bound to the Earth. Near the thermopause is where this gas stops behaving like gas due to lack of collisions, and at the top of the exosphere, reaching from 10,000 kilometers to halfway to the Moon, is where the Sun's radiation pressure on these gas particles overcomes the gravity of the Earth. We are now in true interplanetary space. When I started my Milankovitch cycles video with a reference to Game of Thrones, I didn't realize exactly how apt my analogy was. In that TV show, the armies of the Night King in the north are trapped behind a giant wall. Just like in the TV show, it turns out that on Earth there exists a powerful, icy force to the north that is seeking to overthrow its bounds and rush southward. That powerful winter is also kept at bay by a mighty wall, one that allows the nations to the south to enjoy relatively tranquil conditions. And just like in the TV show, that wall eventually gets breached in a wave of ice that sweeps down and threatens the lives of all those in its way. You might not recognize what I'm talking about. Where is this wall? And what is the icy winter it protects us from? The answer to the first question is a name that I find particularly cool: the polar night jet. And it turns out that the polar vortex it protects us from is a biting chill not to be underestimated. What is the polar vortex, and how does the polar night jet protect us from it? I'm Alex McColgan, and you're watching Astrum, and today we'll learn more about this climate-shattering phenomenon and what happens whenever the polar night jet breaks down and the polar vortex is unleashed. There are actually two polar vortexes, one at each pole of the planet. And even there, each vortex comes in two parts: a tropospheric polar vortex, spinning in the section of the atmosphere known as the troposphere, from ground level up to about 10 to 15 kilometers. This is where 75% of the total mass of the atmosphere resides. Above that lies the stratospheric polar vortex, a technically separate weather phenomenon that has its own size, seasonal cycle, and influence on the global climate. Each of these massive cyclones sits over the pole, spinning with the planet's rotation, with wind speeds that can reach up to 240 kilometers per hour. Why do these winds happen? The first piece of the puzzle is temperature difference. At locations like the equator, where sunlight is most concentrated, the air is warmed and starts to rise. As it does so, it creates an area of low pressure beneath it that draws air into it from its surroundings, like a giant vacuum cleaner. Meanwhile, at places like the poles, where it's much colder, air contracts and falls, creating zones of high pressure, where air molecules want to spread out like a crowd of school children being released into an open field. So naturally, with these two forces at play,
there is a tendency for air to rush from the poles towards the equator. Freezing cold winds are constantly trying to escape from the north and south poles. This model is a little simplified though, as wind does not travel in one continuous line from the pole to the equator. Instead, because air from the equator cools and falls much sooner than the pole at around latitude 30 degrees, and air from the poles warms and rises much sooner than the equator at latitude 60 degrees, there are 3 cells of air on each hemisphere that air circulates in. The polar cells, the air masses above the poles, and the Hadley cells, the air masses above the equator, both cycle in the temperature-driven way I described. However, the middle cell, known as the ferrule cell, is not temperature-driven. Like a gear, it is dragged by the rotation of the other 2 cells and rotates opposite to their motion. In terms of our northern polar vortex, this means that once the air from the pole heads south, it's met by warmer wind traveling in the opposite direction. And when 2 air fronts of different temperatures meet, they clash rather than mix. So the polar vortex is trapped, bounded, clashing against winds coming in from all sides. There's more at play here though. If this was on its own, the cold air from the north would just slide underneath the warm air from the south, not really being trapped at all. There is a second force at play that redirects those winds, spinning them into a vortex that keeps them circling the poles rather than coming down towards the equator. Where does this spin come from? It's due to something known as the Coriolis force. In a simple, flat world, cold wind from the poles would travel towards the equator, while warm wind from the equator would float over it towards the poles. But the world isn't a simple flat sheet. It's a rotating sphere. You are traveling right now at somewhere between 0 km per hour, if you're at the pole and decided to watch an Astrum video while you're there, and 1,600 km per hour at the equator, from the west to the east. You might not notice this fact because everything next to you is, on average, traveling at the same speed in the same direction. But what happens if you were to travel from the equator to the pole? Conservation of momentum states that you would still be traveling eastward at the same speed as previously, but suddenly the Earth beneath you is not traveling quite so fast. Remember, at the pole you'd have 0 eastward speed, but would simply be rotated slowly. If, on the other hand, you keep all your eastward momentum from the equator and travel towards the pole, suddenly it will appear, compared to everything else, like you are traveling east really fast. In practice, this means that air that travels up towards a pole from the equator, whether towards the North Pole or the South, will not go straight up, but over large distances will start to curve towards the east. This rapidly eastward traveling air is why you get jet streams. There are at least 4 of these, straddling the gaps between the Hadley cells, the ferrule cells, and the polar cells. The subtropical jet stream lies between the first 2 and is a little weaker, but the jet streams we are interested in are the polar jet streams, wringing the frigid air off that develops in the north and south poles. These ribbons of air circle the globe in an almost continuous path, a little underneath the boundary between the troposphere and the stratosphere. They are only a few kilometers deep, but can be hundreds of kilometers wide, and in their hearts, the wind can travel at 400 kilometers per hour. As a reminder, over 120 kilometers per hour is getting into strength level of hurricanes. The jet stream around the South Pole is fairly stable. Its powerful winds overrule the polar winds trying to leave the polar air mass, whipping them along with it and dragging the entire polar cell into a massive Antarctica-spanning vortex. At this point, a keen-eyed observer might have noticed a flaw in this model. If conservation of momentum means that air going from the equator towards the pole veers towards the east, why is it that air traveling from the pole towards the equator doesn't do the exact opposite? It has 0 momentum, moving to zones that have considerably more momentum. Comparatively, it should be quickly left behind, appearing to start spinning to the west. This is true, but cold winds have much more friction to contend with as it starts to slide underneath the warm front and then drags along the ground. This seems to slow it down enough that the countervailing jet stream overrules it. It's important to note this tension at play though, as it becomes much more important in the polar night jet. The polar night jet is the jet stream that bounds the vortex at the North Pole. Specifically, it bounds the stratospheric polar vortex, keeping it in check during the coldest part of the year for the North, the polar night. Here, during the winter months, the sun is absent from the sky entirely, creating even more freezing temperatures. Interestingly, this colder climate creates a deeper pressure difference between the air around the pole and the air further south, which actually strengthens the force that creates the polar night jet, meaning that during the coldest part of the year, this freezing air is usually well contained. However, this does not always hold true. There are things that can disrupt a jet stream. There are certain zones, such as the boundary between sea and land, or the presence of a large mountain, that can cause disruption to wind. Coastal environments create their own winds that can suck in jet streams, while mountains force an air current to move around it. Even other weather phenomena, such as El Niño, which you might recognize from one of my recent videos, can have an impact on the path the jet stream takes. As the jet stream is not fixed down, but is a balancing point between a range of opposing forces, hitting such obstacles causes it to deviate from its course. And once it starts deviating, it will rock back and forth like a string that has begun bouncing. It shifts, no longer in its balance, overcorrects itself, and is no longer in balance again, and overcorrects itself again, in massive planetary waves that cause the polar night jet to meander around the Earth rather than travel in a straight line. And these oscillations can reach a point where there is a breach. The first sign of this comes in the form of a sudden stratospheric warming, most common in late winter. An SSW can even represent a time where temperatures rise in the polar region by as much as 50 degrees Celsius over the course of just a few days. Something within the system of the jet stream can be so thrown by this that it leads to the southern moving westerly winds overpowering the jet stream, partially or completely reversing its flow. No longer contained, Arctic wind moves south and meets warmer and warmer air, and pushes faster and faster south in an attempt to balance the gradient. The entire jet stream buckles, and suddenly it pivots. It massively reorients itself, traveling down the planet so that regions like Europe and America, usually safely on the warm, temperate side of the polar night jet, suddenly find themselves in the domain of the polar vortex. The forces of winter have arrived. In fairness, not all of these events are devastating. With sufficient preparation, you can simply put on some warm clothes or try to avoid going outside for the month or so that the polar winds are overhead. As long as you're ready for cold, it's not the end of the world. However, sometimes the outcome is serious. In the UK, in 2009 to 2010, the Big Freeze saw parts of Scotland reaching temperatures as low as minus 22 degrees Celsius, the coldest in nearly 40 years, with widespread transport disruption, event closures, and power failures. Sadly, this in turn led to the death of 25 people. In the US, the 2019 January-February North American cold wave saw a polar vortex move down across much of the country with similar outcomes. Some areas saw temperatures as low as minus 50 degrees Celsius, if you take into account wind chill factor from the blustery, freezing winds. Snowstorms raged. You could get frostbite from being outside in just 10 minutes. Sadly, another 22 people died, with hundreds more needing frostbite treatment. Responsible was the ranging polar vortex. In time, the imbalances in the global temperatures restore themselves, and the jet stream returns to its previous position. However, it's worth noting that some level of jet stream breakdown occurs in the north 6 times every decade. If you live in the northern hemisphere, you will likely see many more of these events over the course of your lifetime, although hopefully not all as powerful as these 2 examples. In the south, you are likely safer. There have only ever been 2 instances in recorded history of the solar polar jet stream breaking down in the same way as the northern one. It has happened though, and the mechanisms behind it are not fully understood. It's difficult to say, as global temperatures gradually rise, what influence this might have on the jet streams. Some evidence indicates that they are traveling further poleward on average year on year, although this is apparently not unheard of in the planet's history. There is some more evidence that the jet streams have strengthened since 2002. If so, we should be grateful. Although unpleasant, the biting cold of the polar vortex usually is only a passing weather phenomenon. We see it return north within a month, but if the jet stream were to go, the polar vortex would come down from the north to stay, and we truly know what it is like to live in Arctic conditions. The more I've learned about this subject, the more I've discovered that the winds of our planet are this fascinating weave of interplaying forces and effects that tug and pull on each other, finding perfect balances and yet constantly shifting in rhythms and patterns. And yet, it does so practically invisibly. So much is going on that we simply do not see down here on the ground, just because air is, well, air. And yet, I've learned its importance. The polar night jet is not just wind with a cool name. It is a bastion of protection, a wall against the frozen wind. It really makes you think of the incredible majesty of the world around us, how much is going on that protects us that we simply do not see. Above our planet's poles, an invisible force is at work. Hypothesized decades before we were able to measure it directly, this global energy force is responsible for sculpting our atmosphere and driving charged particles into space. It's also why some planets end up uninhabitable altogether. It's called the ambipolar field, and it's a force as fundamental to our Earth as gravity or magnetic fields. Although, for the sake of life on Earth, it's a good thing it isn't too strong. Recent breakthroughs from NASA's Endurance mission have finally allowed scientists to solve a 60-year-old mystery by measuring the ambipolar field for the first time, proving once and for all that our planet has a third global energy field. I'm Alex McColgan, and you're watching Astrum. Join me today as we unravel the mystery of our planet's ambipolar electric field, a phenomenon that not only powers the polar wind, but also has an enormous impact on our planet's habitability. Earth's magnetic field, depicted in this video as onion-like layers of lines, helps to shield our atmosphere from dangerous solar energy and damaging cosmic rays. And the gravitational field, shown here as the white glow around our planet, not only keeps us planted on Earth's surface and stops our atmosphere from drifting away, but also provides valuable information in the study of Earth's changing climate, sea level rise, ocean circulation, and much more. As you can see, our magnetic and gravity fields are critical features that help make our planet habitable. And with the recent publication of a 2024 paper in the journal Nature, direct evidence has been found for a third energy field, the ambipolar field. To understand this energy field, we need to talk about plasma. Like a solid, liquid, or gas, plasma is another state of matter, which happens to make up 99% of all visible matter in the universe. Plasma is made of ionized particles and is responsible for several well-known phenomena on Earth like the aurora borealis and lightning. Plasma can form where atmospheric gas density becomes low enough to support the conditions for it, and around 90 kilometers above Earth's surface. This plasma is made up of very lightweight, fast-moving particles, which get trapped along the Earth's magnetic field lines as they move away from the surface. Around the majority of our planet, plasma encounters a barrier that limits its escape into space, known as the plasma pores. Here, plasma co-rotates along with Earth along its closed magnetic field lines. Until the mid-1960s, the prevailing model of our planet's magnetic field theorized that all of the magnetic field lines were closed and the plasma remained trapped. So, what changed? We went to space. In the 1960s, the first spacecraft flying over our planet's north and south poles could actually detect a supersonic wind of charged particles, or plasma, flowing out to space, including positively charged hydrogen and oxygen ions. This observation led scientists to start wondering whether the Earth's magnetic field model should have an open rather than a closed tail. At the time, scientists already knew that our atmosphere lost some particles to space due to thermal escape. This is a type of atmospheric escape that typically happens when the energy from sunlight heats up particles in our atmosphere, allowing them to reach escape velocity and break free of our planet's gravitational pull, kind of like when a pot of water boils and steam evaporates. So it was no surprise that some particles would be escaping into space, but something didn't quite add up. If energy from the sun were the only cause of atmospheric escape, one would expect the particles that were escaping into space to be heated. However, many in the stream were actually cold, with no signs of being heated, and yet they were traveling at supersonic speeds. Scientists hypothesized that there must be another invisible force driving this phenomenon, and in 1968, the term polar wind was coined to describe it, leading to more research and theories into its cause and effects. The idea of a planet-wide electric field was developed to explain the polar wind. But when this was theorized in the 1960s, it was thought that the force was too weak to detect. And at the time, scientists were correct. The electric potential was so weak, it would require very sensitive instruments to measure, and that technology wouldn't be invented for several more decades. Enthusiasm to measure our planet's ambipolar field was spurred again in 2016 after a clue came from the European Space Agency's Venus Express mission. One of the reasons that Earth is hospitable for life is because of its water, while Venus today is dry and barren. However, billions of years ago, evidence suggests that Venus might have had abundant water like our own world does now. This raises the intriguing question: if Venus once had water, where did it all go? The ESA's Venus Express mission offered a potential explanation when it detected a 10-volt electric potential around Venus, at least 5 times larger than expected. This marked the first successful measurement of an electric field on any planet, including Earth. The electric field surrounding Venus could pull positively charged ions like oxygen out of the atmosphere, draining it of the essential ingredients of water, like a vacuum cleaner siphoning particles out to space. Over time, this could have played a role in draining the planet of its once abundant water. This prompted a question much closer to home. Does Earth have a similar electric field? And if so, why has our planet managed to hold onto its water? The electric potential measured around Venus was around 10 volts. For comparison, a standard car battery is 12 volts. But scientists expected our planet's electric potential to be as little as 0.3 volts, similar to a button battery you might find in a watch, and some 25 times weaker than the electric potential on Venus. It's this difference that may be a key reason why our Earth has been able to keep its water. And that's what inspired NASA's Endurance team to develop a new type of scientific instrument called a photoelectron spectrometer to find Earth's weak electric field. The instrument is designed to measure the speed of electrons escaping from Earth's atmosphere as a way to reveal our planet's electric potential. Earlier, I explained thermal escape, and I mentioned that particles are able to escape from our atmosphere when they reach escape velocity. That escape velocity is a very specific, predictable speed, but this speed should be ever so slightly slowed by Earth's electric potential. And so, by measuring that slowing effect at apogee, or the furthest point in Endurance's orbit from Earth, the instrument would be able to measure the strength of the electric potential around our planet. Such a sensitive instrument would need to be launched at precisely the right location and time in order to ensure a chance at making the observation successful. The Svalbard rocket range was selected for the job. It's the northernmost range in the world, located in Svalbard, Norway, a group of islands in the Arctic Ocean. Here, the NASA Endurance team would be able to launch the instrument on a suborbital rocket through Earth's magnetic North Pole. And on the 11th of May 2022, the team of international scientists did just that. Named after the ship that carried Ernest Shackleton's crew in their 1914 attempt to reach the South Pole and cross Antarctica, the Endurance mission launched its suborbital rocket to an altitude of 768 kilometers, collecting data over 518 of those kilometers before splashing down 19 minutes later in the Greenland Sea. During its flight, the instrument measured a change of 0.55 volts in electric potential between 250 kilometers and 768 kilometers. Space scientist Glenn Collinson, the principal investigator for NASA's Endurance mission, said even though half a volt is almost nothing, again almost about the strength of a watch battery, it's just the right amount to explain Earth's polar wind. This first ever direct measurement of Earth's electric field marked a pivotal moment in our understanding of this fundamental planet-wide energy force. The ambipolar field exists in what's called the ionosphere, a region that stretches across 3 out of 5 of our atmospheric layers. Our atmosphere is divided into 5 main layers. The troposphere, also known as the lower atmosphere, only reaches about 20 kilometers above Earth's surface and is where the majority of weather occurs. Next is the stratosphere, which extends up to about 50 kilometers and contains most of our planet's ozone that protects us from ultraviolet radiation from the sun. This layer has very little circulation and is where commercial airlines usually fly. Above the stratosphere is the mesosphere, extending up to about 85 kilometers. This is where meteors burn up near the bottom of the mesosphere layer are thick enough to slow them down. It's within the upper reaches of the mesosphere that the ionosphere begins, but its influence stretches far beyond that. Starting around 80 kilometers above the surface in the mesosphere, the ionosphere continues outward through the entire thermosphere layer from about 85 to 600 kilometers. This is where auroras happen, and high-energy ultraviolet and X-ray radiation are absorbed, creating charged particles. And finally, the ionosphere ends in the lower exosphere, which begins around 600 kilometers and continues out to about 10,000 kilometers from Earth's surface, where it fades into outer space. The exosphere is where many satellites orbit around our planet. As you can see, the ionosphere starts around 80 kilometers above sea level and stretches hundreds of kilometers into space, where it overlaps with Earth's magnetosphere, a region of space surrounding Earth. Within this massive region of the ionosphere is where we find the ambipolar field, which is theorized to begin at around 250 kilometers. While most of our atmosphere is composed of nitrogen, the upper region of our ionosphere is home to lighter elements like oxygen, hydrogen, and helium. When photons from the sun collide with these elements in the upper atmosphere, they can knock electrons loose from the elements in a process called ionization, leaving positively charged particles called ions and negatively charged electrons. Because of the opposite charges of the negative electrons and positive ions, they are attracted to each other and become tethered together by an electric field. It's this electric field that constitutes a major part of the ambipolar field. The electrons within the electric field are so light that the slightest push could send them flying out to space, while the ions are more than 1,800 times heavier than the electrons and sink toward the ground due to gravity. The subatomic tug of war works in both directions, but the upward tug from the energized electrons is able to just slightly overwhelm the force of gravity on the ions. This outward pressure of ionospheric electrons is what creates the ambipolar field, depicted here as the sparkling blue glow around our planet. The upward lift inflates our planet's ionosphere and accelerates some ions enough to escape from the atmosphere, creating the polar wind along our poles' magnetic field lines. What's more, the ambipolar field can achieve this acceleration of plasmas without heating them, providing an explanation for the cold plasma scientists had detected escaping from the ionosphere. It's the bidirectional nature of the interaction between ions and electrons that gives the ambipolar field its name. The Latin prefix ambi means both, and polar refers to the polar regions, where the electric field's effects are felt the strongest. Collinson, the Endurance mission's primary investigator, called the ambipolar field an agent of chaos, stripping particles from our atmosphere away into space. Hydrogen ions make up the majority of the polar wind. They are so light, the ambipolar field's upward force of these electron ions is 10.6 times stronger than the force of gravity, leading the ions to accelerate up at supersonic speeds and escape from our atmosphere above the Earth's magnetic poles. Scientists have found that our planet loses about 3 kilograms of hydrogen gas every second, or 95,000 tons per year. Additionally, the Earth also loses about 50 grams of helium per second, or 1,600 tons of helium gas per year. A smaller but still measurable amount, and a much smaller amount of other gases like oxygen. However, not all of this is due to polar winds. It occurs through a combination of factors, including thermal escape and non-thermal escape mechanisms such as polar wind. But don't worry. Despite our planet losing several thousand tons of its atmosphere to space every day, we are nowhere near running out of air. The planet won't run out of oxygen for 1 billion years. It will be another billion years after that before our oceans will have been depleted of most of their hydrogen. Around 4 billion years from now, our planet may look very similar to how Venus looks now. All of our water will have evaporated, and the greenhouse effect will have become strong enough to melt rock, leaving our planet a dry, lifeless world. Keep in mind that modern humans have only existed on this planet for around 300,000 years. Our species would need to exist more than 3,300 times that length to be around in 1 billion years. While not really important on human timescales, it is still interesting to think about though. And while hydrogen ions may be the lightest and most common type of ion to escape in a polar wind, heavier particles also get a boost from the ambipolar electric field, helping to shape our atmosphere's structure and dynamics. How exactly? Well, now that we've measured the ambipolar field, scientists can delve into all the ways the ambipolar field shapes our atmosphere. Take oxygen ions for example. These heavy ions weigh half as much when they're immersed in the 0.55 volt ambipolar field. This effect increases the ionosphere's scale height by 271%, which means our atmosphere can remain denser at greater heights than it would otherwise be able to. Endurance's discovery and measurement of the ambipolar field also provided an important key to understanding why Earth has been able to hold on to much of its water up until this point, while our neighbouring planet Venus was not able to do the same. It's theorized that any planet with an atmosphere may also have an electric field, and you may recall that earlier I said Venus's electric potential was measured to be around 10 volts, roughly 18 times stronger than the ambipolar field on our own planet. While Earth does lose a constant flow of particles to space, both through the polar wind as well as other types of atmospheric escape, this effect would have likely been much more pronounced on Venus because of its stronger electric potential, leading to the loss of heavier particles like the ones that make up water. The fact that our ambipolar field is so weak may be an important part of why our planet has been able to hold onto its water. We've only just started to explore the depths of how the ambipolar field has influenced our planet and life on Earth. And the endurance scientists have said there are already plans for additional measurements of our planet's ambipolar field in the future. Like its predecessor, the new rocket will also carry the legacy of a long-past Arctic explorer, named after the Resolute, a ship that set off to explore the Arctic in 1850. And now that we've finally been able to confirm and measure the ambipolar field strength, and with a follow-up mission already planned to take more measurements, scientists can start asking some of the bigger and more exciting questions, like what it means for Earth's complex atmospheric dynamics, and how it helps to govern planetary evolution. And doesn't the potential insights we stand to gain from this research feel electric? When it comes to talking about the universe, I'm not usually at a loss for words. But every so often, I see something so awe-inspiring and unusual that words don't do it justice. And it seems that when I posted an image of this last year, it looks like I'm not alone here. Such is the case with Noctilucent clouds, a strange and beautiful phenomenon that occurs high in the Earth's mesosphere and requires a unique set of conditions to form. In fact, these cloud formations are so captivating that they've inspired communities of watchers who share atmospheric data online in the hope of seeing one for themselves. So, what are Noctilucent clouds? What gives them their ghostly luminescence? And what surprising insights can they offer, not just about Earth's atmosphere, but perhaps the future of our planet? I'm Alex McColgan, and you're watching Astrum. Join me today as we view spectacular images of these eerily beautiful cloud formations, learn how they form, and understand why they are giving scientists a surprising window into Earth's changing atmosphere. Imagine a clear summer night. The sun has dipped below the horizon and Capella is shining brightly to the north. Suddenly, a bright streak erupts low in the northern sky. It might look like a shining silver thread, or perhaps an icy blue whirl. Slowly, the streaks get brighter and clearer, until finally, the whole sky glistens with a patchwork of eerily shining clouds. Night shining clouds such as this formation, photographed over the Baltic Sea, are truly spectacular. And no, they don't actually emit light. They get their glowing appearance by reflecting solar radiation during astronomical twilight, when the sun is between 6 and 16 degrees below Earth's horizon and remnant light is scattered in the upper atmosphere. Because Noctilucent clouds form at very high altitudes, around 76 to 85 kilometers above the terrestrial surface, they can reflect the sun long after an observer has fallen into Earth's shadow. So, while Noctilucent clouds also form during daylight hours, they are only visible to the unaided eye at night. To make a Noctilucent cloud, you need water, dust particles, and incredibly low temperatures. Unlike normal clouds, which form in the Earth's troposphere, where 75% of the atmosphere's mass and 99% of its water vapor occurs, Noctilucent clouds form high in the upper mesosphere, which is the atmosphere's third layer above the stratosphere. Just a reminder, the lowest layer of atmosphere on the Earth is the troposphere, the boundary of which is the tropopause. Then the stratosphere, stratopause, mesosphere, mesopause, thermosphere, thermopause, and then finally the exosphere. For more about all these layers, check out this video. The mesosphere is a tricky region to study, since it's too high for spacecraft to fly and too low for orbital spacecraft due to atmospheric drag. Noctilucent clouds form slightly below the mesopause, which is the upper boundary between the mesosphere and the thermosphere. The mesopause is also the coldest region of Earth, with temperatures that can plummet below 100 degrees Celsius. By comparison, the coldest temperature ever recorded in Antarctica was minus 89.6 degrees Celsius. These frigid conditions produce tiny ice crystals less than 100 nanometers in diameter, which then gather on dust particles. Researchers have learned that the mesosphere must reach minus 120 degrees Celsius for these ice crystals to form. That's pretty cold. But if noctilucent clouds require such cold conditions, why do they occur during summer? Well, one unusual property of the mesopause is that it is colder in summer than in winter. Known as the mesopause anomaly, this happens because hot air in the lower troposphere expands, resulting in upswelling gases that decompress in the mesosphere, causing adiabatic cooling. Because noctilucent clouds require very low temperatures, they only appear for 60 to 80 days out of the year, peaking around 20 days after the solstice. If you want to see a night shining cloud formation, you'll need a lookout spot between plus or minus 50 and 70 degrees latitude. Although satellites have spotted many mesospheric clouds north of the 70th parallel, here on Earth, the polar regions have too much ambient light during the summer for optimal viewing. So if you happen to live in northern Norway or Alaska, you'll have to travel south for your noctilucent cloud watching. That's a pretty good survey of what we know, so let's talk about what we don't. Saying the mesosphere is a very dry place would be a bit of an understatement. In fact, it is 1 million times drier than air from the Sahara Desert. Not exactly a place you'd expect to find clouds. We currently think upswelling air from the troposphere is the likely cause of this moisture. More puzzling, however, is the question of where the dust is coming from. One theory is that it comes from space in the form of debris. The Earth gets bombarded daily with thousands of meteorites and other space debris. Could they leave enough dust to create such massive cloud formations? Or could there be other causes? Interestingly, noctilucent clouds were first sighted in 1895, 2 years after Krakatoa's massive volcanic eruption in Indonesia, which spewed debris into the upper atmosphere. It has to be something big like this, because otherwise the atmospheric layers don't mix very much, and so dust wouldn't usually make it to the mesosphere. We also know that man-made sources, such as exhaust from space shuttles, can sometimes trigger noctilucent clouds, such as a 2014 incident when the SpaceX Falcon 9 caused noctilucent clouds over Orlando, Florida. In 2009, the United States Naval Research Laboratory successfully created an artificial noctilucent cloud using exhaust particles from a suborbital sounding rocket. And in 2018, the University of Alaska created a noctilucent cloud by releasing water from a suborbital rocket. But without such proximate causes, the source isn't easy to pinpoint. Luckily, NASA has launched a satellite known as the Aeronomy of Ice in the Mesosphere, or AIM, to answer these and other pressing questions. It was first launched in 2007, but as of 2022 is still operational. AIM is powered by 2 solar panels and is equipped with 3 payload instruments: the Cosmic Dust Experiment, which emits pulses to measure speeding dust particles; the Cloud Imaging and Particle Size has 4 cameras that image mesospheric clouds from variable angles to create a detailed 2D panoramic view; and the Solar Occultation for Ice Experiment, which measures particles, temperature, and atmospheric gases in order to identify chemicals and conditions for noctilucent cloud formation. There have also been several experiments to synchronize AIM's observations with those of low-flying aircraft, the first of which was conducted in July 2009. By synchronizing data between satellites and aircraft, scientists can construct far more detailed models of mesospheric cloud formation and their features than they could from AIM alone. For NASA and other atmospheric researchers, answering these questions is no idle matter. The mesosphere is a remarkably sensitive indicator of changes that are happening elsewhere in the atmosphere. The same features that make it so unusual, its rarefied gases and sensitivity to changes far down in the troposphere, make it a useful canary in the coal mine, so to speak. Decades of noctilucent cloud study have made it clear that they are becoming more frequent, and climate researchers are now beginning to link changes in noctilucent cloud distribution to global climate change. As the troposphere gets hotter, the mesosphere, vis-a-vis the mesopause anomaly, may well be getting cooler. And improving our understanding of the mesosphere has other far-reaching implications as well. It is a vital part of the atmosphere for re-entering spacecraft. And because the mesosphere is so dry and low density, studying it could help us learn about atmospheres on other planets, such as Mars. By deepening our knowledge of the mesosphere, researchers hope not only to understand the properties of noctilucent clouds, but also Earth's atmosphere as a whole and how it is changing over time. Picture the ocean on a dark and windy day. Rather than smooth, rolling waves, the surface is rough and choppy, with deep troughs and frothy crests. Now, imagine that stormy ocean flipped upside down and blanketing an entire sky. It may sound crazy, but that image is a pretty close approximation of Asperitas clouds, an extremely rare cloud type that was only recognized by the World Meteorological Organization in 2017. Asperitas, which translates to rough and uneven, is one of the rarest cloud forms on record, and the only one to have been formally added to the WMO's Cloud Atlas in almost 70 years. Given how recently they were discovered, not much is known about how or when Asperitas clouds form, although we have some theories. So, what makes Asperitas clouds different? Why haven't we noticed them before? And could their discovery provide a blueprint for identifying extremely rare weather events in the future? I'm Alex McColgan, and you're watching Astrum. Join me today as we look at spectacular, high-definition images of Asperitas clouds. Learn what scientists think could be giving them their dramatic appearance, and explore the exciting implications of this unusual convergence of citizen science and trailblazing research. In 2006, Jane Wiggins, an amateur photographer located in Cedar Rapids, Iowa, took a photo from her office window that she described as looking like Armageddon. She sent the image to the Cloud Appreciation Society, which posted it on their website. The photo immediately set off shockwaves among cloud watchers, who suspected that it could be evidence of a previously unknown cloud formation. Other amateur hobbyists using the Cloud Spotter mobile app started sharing their images with each other, sharing weather conditions to look out for to help others see it for themselves. This caught the eye of the Royal Meteorological Society, which used dozens of photos collected by the Cloud Appreciation Society to prepare a case that they sent to the World Meteorological Organization. After several years of debate, the WMO made an announcement. For the first time since 1951, they were adding a totally new type of cloud to the Cloud Atlas, giving Asperitas clouds the unique distinction of being the only cloud type to have been discovered as a result of digital crowdsourcing. But why was this rare? And who decides what makes a cloud form unique? Let's start with a primer. Clouds, essentially, are liquid droplets or solid particles suspended in the atmosphere of a planetary body. While on other planets, clouds can be made of methane, ammonia, or even sulfuric acid, here on Earth, the vast majority contain liquid or frozen water. And personally, I'm glad we don't have many of the sulfuric acid variety. Clouds form when saturated air reaches its dew point, the temperature at which, under a given set of barometric conditions, water vapor condenses into liquid due to cooling air or increased saturation from an adjacent water source. There are 5 primary cloud types: stratus, cumulus, stratocumulus, cumulonimbus, and cirrus, each of which are subdivided into different genera based on altitude. However, in addition to these primary categories, there is a range of accessory clouds, which are clouds that become detached from the original genus clouds, as well as supplementary features. All of these are formally classified in the WMO Cloud Atlas, the International Manual for Cloud Identification, which uses a Linnean nomenclature that has been in place since the 19th century. The WMO is responsible for updating the Cloud Atlas, but revisions are extremely rare. The last new formation was Cirrus Intortus, added back in 1951. Now, Asperitas clouds are thought to be mostly a supplementary feature of stratiform clouds, which are low elevation layered clouds without vertical development, although Asperitas have also been observed to be stratocumulus or altocumulus. Interestingly, while the bases of the stratiform clouds are generally flat, they tend to develop significant features at the top due to wind and temperature changes. This is extremely common, and something you will no doubt be familiar with if you've looked out of the window of a plane. What makes Asperitas clouds unusual is their highly developed structures at the bottom. In 2017, researchers from the Cloud Appreciation Society, University of Reading, and McGill University published a paper attempting to describe the features and causes of Asperitas cloud formation. According to the authors, Asperitas clouds are defined by their rough, somewhat wave-like cloud base that lacks the smooth, undulating shape of the, possibly related, undulatus cloud type. Given these semi-wave-like characteristics, the authors hypothesize that Asperitas clouds are likely created by weak oscillatory activity. There are a few potential causes of this. One is orography, which is the wave-like movement caused by the flow of air over mountainous terrain. However, there could be other reasons, such as horizontal wind shear, convection, which is the exchange of matter or temperature between fluid bodies, or atmospheric gravity waves. By the way, in case you're wondering, a gravity wave isn't the same as a gravitational wave. As much as I love space-time physics, we're not talking about massive ripples in the space-time fabric here. A gravity wave occurs at the border between one fluid and another, when a force upsets the equilibrium and gravity tries to restore it, which produces a back and forth movement, or wave orbit. Some familiar examples of gravity waves include tsunamis and the changing tides. You have probably seen the result of gravity waves affecting clouds too, undulatus clouds. I'm sure you've noticed cloud formations like this before from a ground view. The view from space is equally spectacular. But Asperitas clouds have an appearance of roughness that indicates unusual instability at the cloud base. These aren't smooth and wave-like like the undulatus cloud type we've just looked at, but have a formation that is chaotic, like the stormy ocean we talked about earlier. While stratiform clouds often have what is known as Kelvin-Helmholtz instability at the top, an instability that comes from velocity shear within fluids, this instability is more unusual at the base of clouds. So what might be the cause? We don't know yet, but the authors of the 2017 paper from earlier suggest that this instability may propagate downward from the top of the cloud, which could happen if the cloud is thin enough. Perhaps there are different reasons each time. The scientist who captured this time-lapse said that here, gravity waves were moving through an inversion underneath an elevated region of instability. You've probably seen an inversion before, where clouds or even smog is trapped under a layer of hotter air. Thunderstorms were in the forecast, but the thunderstorms could not pull their inflow air from near the surface due to the inversion, so instead, they pulled from above the inversion. The gravity waves moving through the inversion created enough lift that a strong updraft was formed, and it moved in phase with the peak of the gravity wave. This enhanced lift from the updraft increased the amplitude of the wave and made the Asperitas cloud here very visually impressive. Regardless of how it happens, this internal instability appears to disrupt the weak oscillatory activity at the base, resulting in the rough, choppy appearance. So, when you think about it, the winds and currents causing the choppiness of the ocean on a stormy day aren't that unlike the chaotic forces scientists think are producing instability in an Asperitas cloud. In both cases, complex fluid dynamics are in play, giving rise to eerily similar characteristics. Nature may not repeat itself, but it often rhymes. So, there you have it. A primer on one of the newest and least understood cloud types on record. If this interests you, you might want to keep watching the sky and taking photos of anything interesting you see. Who knew we'd still be discovering new cloud types? What else out there don't we know about? And who knows, you could be part of the next scientific breakthrough. Have you ever looked up at the sky and seen something so strange it made you wonder if you were dreaming? Perhaps you saw what looked like a rainbow, only it was upside down. Or maybe you saw a perfect circle of light around the sun with 2 splashes of rainbow color on the sides. Well, no need to pinch yourself. What you are seeing is a unique category of optical phenomena called ice halos. Although similar, they aren't technically rainbows, but their own distinct wonder. Some are relatively common, while others are extremely rare. As you might know, rainbows occur when sunlight is refracted by water droplets suspended in the atmosphere. When light travels from one transparent substance to another, such as from air to water, its speed changes, bending its path and separating the light into colored bands by wavelength, a process called dispersion. But what happens when light hits water particles that are made of ice rather than liquid water? Well, depending on the shape and orientation of the ice crystals, as well as the direction of the light hitting them, they can produce a whole range of optical phenomena. To date, 119 kinds of ice halos have been categorized, and there might still be others we don't know about. So what are ice halos? How do they form? And what should you look for if you want to see one for yourself? And finally, are they a sign of something more ominous on the horizon? I'm Alex McColgan and you're watching Astrum. Join me today as we look at spectacular images of some of the better known ice halos and get to the bottom of how and why these delicately beautiful spectacles appear. This stunning photograph shows a 22-degree solar halo spotted over Großkrotzenburg, Germany. 22 degrees doesn't refer to air temperature, but to the angular radius of the halo. To visualize this, imagine drawing a direct line from a point on the halo to the observer's eye. Then do the same from the sun at the circle center to the observer's eye. The angle between these two sight lines is 22 degrees. Hence the name 22-degree halo. There are also 46-degree halos, which, as you might guess, are larger than their 22-degree cousins, but are also fainter. Halos can also occur in moonlight, as you see here. These eerily beautiful halos are called moon rings or winter halos, but they're technically the same optical phenomenon. What distinguishes them from solar halos is the source of light. In some images, you may notice that the patch of sky inside a halo appears darker than the sky outside the ring, a dramatic effect that is sometimes described as a hole in the sky. This happens because, when light bounces and refracts off the ice crystals, none of it is reflected toward the light source, which, to an observer, leads to an apparent darkening inside the halo. But this is just the tip of the iceberg, because ice halos take on all kinds of strange and shocking forms. Spots of vibrant color, upside down rainbows, and even upside down rainbows at night. But before we get there, let's take a moment to break down the fascinating optics that produce these strange occurrences. Most circular halos are made by water crystals in cirrus or cirrostratus clouds. These clouds occur high in the troposphere, usually 5 to 10 kilometers above the Earth's surface, where temperatures are very cold. As a result, halos can be seen anywhere on Earth all year long, even in very hot climates. Atmospheric ice crystals are small, usually less than 10 micrometers long, and uniform in size and shape. This extreme regularity has to do with the structure of ice on a molecular level, and is necessary for making halos. You see, water molecules consist of 2 hydrogen atoms and an oxygen atom. In liquid water, the bonds between hydrogen atoms are weak, so the bonds are constantly breaking and reforming as the molecules slip past each other. But when water freezes, that molecular movement slows to a halt, and the bonds between hydrogen atoms become fixed. This results in a hexagonal lattice structure known as a tetrahedral arrangement. This highly organized structure on the molecular scale is what causes the ice particles to form hexagonal crystals. Some crystals are flat, like plates, whereas others look like columns with a hexagonal cross-section. Despite this variation, these crystals behave so uniformly because of their interfacial angles. In fact, the angles between any two faces of ice crystals are completely identical. It's this extreme regularity of the interfacial angles, rather than the crystal's mass or shape, that allows millions of particles to scatter the light with the consistency needed to produce a halo. Halos are sometimes quite colourful. That's because when ice crystals refract light, the red and blue frequencies bend at slightly different angles and disperse. Some 22-degree halos have two colourful spots visible to the left and right of the sun. These beautiful looking phenomena are called parhelia, or sundogs. Sundogs appear when ice crystals that are shaped like hexagonal plates take on a horizontal orientation. As I mentioned earlier, some crystals form as thin hexagonal plates, whereas others form as columns with hexagonal cross-sections. When plate-shaped crystals form and settle downward, atmospheric drag orients them horizontally, with the c-axis you can see pictured almost perfectly perpendicular. Larger plates tend to wobble just a bit more than smaller ones. This wobble, in turn, affects how tall sundogs appear to be, with wobblier plates causing the sundogs to appear more vertically stretched. Sundogs are sometimes accompanied by another optical phenomenon called a circumzenithal arc. These arcs look similar to rainbows, only they're upside down, which gives them a friendly, smiling appearance. These arcs appear over the sun only when the direction of light and the orientation of the ice crystals are just right, when light enters the top faces of hexagonal plate crystals and exits the side faces. However, this can only happen when the sun is lower than 32.2 degrees above the horizon and more than 5 degrees. Because the ice crystals function essentially like a 90-degree prism, the color separation is excellent, meaning circumzenithal arcs have a far higher degree of clarity than actual rainbows. And if you're really lucky, you might even spot one with moon rings. Called lunar circumzenithal arcs, these unusual arcs only appear when the moon is extremely bright and fairly low on the horizon. As strange as it sounds, it is possible to see what looks like an upside-down rainbow at night. Now, this is amazing. Circular halos have also been sighted on Mars. Here is an image taken by Perseverance on the 15th of December 2021. This has led some to suggest that the cause may be carbon dioxide crystals in the planet's cold, thin atmosphere, or perhaps a mixture of CO2 and water ice. We didn't always know that halos occurred on Mars, so as you can imagine, the Perseverance team was pretty excited to see this. Because the size and appearance of the halos provide clues about the types of crystals forming in the atmosphere, scientists hope that studying halos here on Earth and spotting them on other planets could shed light on the composition of those planets' atmospheres. As a result, more research will be undertaken in the future to document and understand the appearance of ice halos on Mars, as well as other moons and planets. So there you have it, a primer on some of the better known ice halos and their associated optical phenomena. And if you want to see one for yourself, here are some things to look for. First, check for cirrus clouds. These are the high altitude, wispy clouds that contain the small ice particles needed to produce ice halos. Second, look for the sun or moon, but take care not to stare directly at the sun, kids, because that can damage your eyes. While rainbows form around the anti-solar point, which is located directly opposite the sun in the celestial dome, most ice halos form in proximity to the sun or moon. And while ice halos tend to appear in fair weather, they often arrive at the front of an approaching storm system. Meaning, if you see one, it's better not to linger outside for too long. Head indoors and find somewhere cozy to enjoy the upcoming storm. So, if the weather is fair, but you see rain in the 24-hour forecast, keep an eye on the sky. Your chances of seeing a halo will be higher. Of course, the best way to see one is to look every day. Ice halos can form anywhere on Earth, so if you keep looking up, you're bound to see one sooner or later. But when it comes to ice halos, there's plenty more to talk about. There are a lot of other strange and even rarer kind of halos, and probably more yet to be discovered. So if this is a topic you'd like to see more about in the future, and if you've seen them for yourself, I'd love to hear about it in the comments. Imagine seeing a glowing light suspended in the air. It looks almost like a duplicate sun, blindingly bright and fixed at some point low on the horizon. Suddenly, the clouds pass overhead and the dazzling light vanishes like vapor. No, this isn't a scene from a fantasy movie, but an optical occurrence called a subsun, which is one of several uncommon kinds of ice halos. If you watched my previous video on ice halos, then you already know a few of the better known types. A quick recap: halos are optical phenomena that appear when light hits tiny ice crystals that are suspended in the atmosphere. Scientists have identified 119 kinds so far, and there may be others we don't know about. Today we'll look at a few of the rarer and most unusual kinds of ice halos. As you'll see, these phenomena can be very strange, and the best way to understand them is as optical illusions that don't truly exist in space. Nonetheless, if you happen to be in the right place at the right time, you'll be treated to some of the dazzling sights that test the boundaries of what is real and what is an illusion. I'm Alex McColgan, and you're watching Astrum. Join me today as we look at stunning high-definition images of some of the rarest and most unusual ice halos, including subsuns, Bottlinger's rings, light pillars, and more. Let's start with a little primer. Ice halos are produced by water crystals that are usually found in cirrus or cirrostratus clouds. Cirriform clouds occur high in the troposphere, usually 5 to 10 kilometers above the Earth's surface, where temperatures are very cold. These ice crystals are very small, usually less than 10 micrometers long, and always have uniform interfacial angles. So uniform, in fact, that the angles between any two faces in an ice crystal are completely identical. However, despite this angular regularity, ice crystals vary in size and shape. Some crystals are flat, like hexagonal plates, whereas others form as columns with a hexagonal cross-section. The subsun we looked at earlier requires plate-shaped crystals to occur. As the plate crystals settle downward, atmospheric drag orients them parallel to the Earth's surface, much like how sundogs occur. Subsuns form when disturbances in the air introduce a wobble to these plate-shaped crystals. The more wobble the plates have, the more vertically elongated the subsun will appear. Occasionally, there is so much vertical elongation that the plates produce a categorically distinct type of halo known as a sun pillar. These only appear when the sun is between 20 degrees and 6 degrees above the horizon. However, while sun pillars might look like beams of light shooting from the ground, this effect is deceiving. What's really happening is that the plate crystals act like millions of tiny mirrors, which bounce the light rays towards the observer along a vertical axis. These scattered rays then produce a diffuse reflection visible to an observer as a pillar of light. A similar effect happens when the sun sets over water, bouncing a diffuse reflection off the water surface that sometimes looks like an elongated pillar. What do you think? Can you see a resemblance? Sometimes light pillars can appear when the moon is the primary light source. As you might have guessed, these are known as moon pillars. This image shows a beautiful one captured by the European Space Agency over Antarctica. However, when the conditions are right, light pillars can come from all kinds of sources, even artificial ones. On occasion, this has led to some dramatic scenes. In this photo, low-forming ice crystals called diamond dust have settled close to the Earth's surface, creating a spectacle that looks almost like an alien arrival. And if you haven't heard about the peculiar effects of tiny ice crystals suspended in the Earth's atmosphere, you can hardly be blamed for jumping to conclusions. I wonder how many eyewitness accounts of mysterious lights can be explained by halos like this one. Let's look at a different but equally strange phenomenon called Bottlinger's rings. First documented during a hot air balloon flight in 1909, Bottlinger's rings usually last for only a few seconds, although occasionally they can be visible for upwards of an hour. They typically appear as shimmering elliptical rings around the sun, but due to the sun's intense glare, they are more likely to be sighted around dimmer subsuns. Most sightings of them tend to occur in airplanes. Bottlinger's rings were originally thought to be produced by plate crystals that had developed a gyrational motion. However, simulations have recently shown that the effect can be more effectively reproduced by pyramidal-shaped crystals, with a small amount of wobble. Still, there's a lot we don't know about Bottlinger's rings, and the current theories are mostly educated guesswork. The pyramidal crystals that work in simulations have very wide apex angles, such that they take on a flat, almost plate-like appearance. The problem is that these shapes are unlikely to form naturally from ice's molecular lattice structure. All we really know is that these elusive halos are extremely rare. Lastly, I'll leave you with a rare cousin of the circular halo called superlateral arcs. Unlike 22-degree halos, superlateral arcs never form from a complete circle, although they sometimes form at the same time as circular halos, producing a complex halo effect. Superlateral arcs appear as colored bands above the sun, but never reach below it. When their colors are visible, red is the closest band to the sun, with blue on the outer edge. We think superlateral arcs form because of hexagonal rods or column-shaped crystals when light enters the base and refracts through the prism side. While these arcs are sometimes confused with 46-degree halos, which are a larger cousin of the 22-degree circular halo, they are a separate phenomenon that visually resembles rainbows due to their arc shape and sometimes colorful appearance. In recent years, researchers have documented a number of weird atmospheric phenomena on Earth that were previously unproven or even unknown. There are transient luminous events like red sprites, blue jets, gigantic jets, and elves. There are noctilucent clouds, and rarely seen variants of familiar phenomena like green lightning and red auroras. These are just a few of the incredible occurrences we've been able to observe and verify. Yet, despite amazing advances in our technology and research capabilities, there are still phenomena that are almost completely outside our ability to prove them. Of these, none is stranger and more terrifying than ball lightning, an alleged electrical occurrence so mind-boggling that it sounds, well, made up. Ball lightning has been reported so many times and receives so much scientific scrutiny that it occupies an unusual place between science and folklore. But, unlike most myths, ball lightning has a mounting body of evidence that suggests we should not only take its existence seriously, but we might already have proof that it does. So, what is ball lightning? How are scientists attempting to reproduce it in laboratories? And if it is a real phenomenon, as many experts believe, why is it so difficult to prove? I'm Alex McColgan, and you're watching Astrum. Join me today as we look at the fascinating history of ball lightning encounters, examine some of the most intriguing new theories out there, and learn about stunning laboratory experiments that are attempting to get to the bottom of one of science's strangest unsolved mysteries. For centuries, accounts of ball lightning have come from all over the world. The stories vary, but many agree on certain details. The phenomenon appears as a bright burning orb, sometimes golf ball sized and sometimes much larger. It's usually white or blue, but can also be red, orange, or yellow. The phenomenon is said to last between 1 and several seconds, float in a slow path, at times changing direction, sometimes even erratically, and has been alleged to pass through walls and windows unscathed. According to some reports, the ball lightning fizzles, In others, it explodes violently, causing severe damage, leaving behind an odor that has been described as sulfurous. At its most destructive, ball lightning has been reported to maim and kill people, and to blast apart heavy walls, doors, and ships. Now, on this channel, we don't accept anecdotal evidence as proof, no matter how compelling. Only observation, controlled testing, and repeatability can confirm a phenomenon scientifically. So, with that in mind, let's look at a few of the alleged ball lightning encounters I find most intriguing. In 1739, the Catherine and Mary were sailing down the Gulf Coast of Florida when it ran into a deadly thunderstorm. According to an eyewitness, a large ball of fire fell from the element and split our mast in 10,000 pieces, killed one man, another had his hand carried off, and had it not been for the violent rains, our sails would have been a blast of fire. That's quite a story, but it gets weirder. In 1753, Georg Richmann, a renowned professor and electrical researcher, was attending a conference in St. Petersburg when he saw a storm approaching. Bringing an engraver to record his observations, he hurried to conduct a kite experiment like the one Benjamin Franklin had performed the previous year. As reported afterwards by the engraver, Richmann was conducting the experiment when a fiery blue orb crawled down the string, fatally striking him and knocking the engraver unconscious. The reported autopsy found a coin-sized red mark on the professor's forehead and injuries consistent with electrocution. But maybe the most compelling eyewitness account comes from 1963, when R.C. Jennison, a researcher at the University of Kent, was flying late at night from New York to Washington. Jennison was sitting in the cabin shortly after midnight when the plane became enveloped in a bright electrical discharge. Within seconds, a bright glowing sphere about 20 centimeters in diameter emerged from the pilot's cabin and traveled the length of the aircraft. In 1969, Jennison published his observations in precise detail in the pages of Nature magazine. Due to credible reports like Jennison's, scientists have taken the phenomenon seriously and put forward numerous models to explain it. One theory proposes that ball lightning could be a hallucination triggered by the magnetic field close to a lightning strike. Citing similar hallucinations experienced during epileptic seizures, this theory suggests that ball lightning could be a figment of the stimulated occipital lobe. However, if true, it would seemingly contradict reported damages caused by ball lightning, such as the death of Georg Richmann. Another hypothesis proposes that ball lightning is a contained plasma reaction, like St. Elmo's fire, the phenomenon famously observed on the masts of ships, when the voltage between the air and the ground is great enough to break the air molecules into highly excited particles. According to this theory, the plasma in ball lightning becomes a self-contained bubble that behaves as a soliton, a self-reinforced wave that maintains its shape and moves at constant velocity. Don't worry if you find this confusing. We're touching on a pretty complicated subject that even researchers are still struggling to understand. One of the most promising hypotheses was proposed by John Abrahamson and James Dinnis at the University of Canterbury, Christchurch in the year 2000. This model proposes that a powerful positive lightning strike can vaporize molecules in soil, causing energized nanoparticles that then react with oxygen in the air to produce light and heat. And remarkably, this model is supported by a strange incident that occurred 10 years ago in Lanzhou, China. Remember when I said that there weren't any verified recordings of ball lightning? Well, that may not be entirely true. In July 2012, researchers from Northwest Normal University had set up spectrometers to record ordinary lightning when a powerful lightning strike produced a glowing white orb. The orb had an estimated glow 5 meters across, which turned red as it traveled for 10 meters before ascending into the air. All this was recorded with high-speed video, which sadly hasn't been made public. and the spectrometer reading, which has. The spectrometer confirmed emission lines from silicon, calcium, and iron, all common in soil. So, if this observed phenomenon was in fact ball lightning, as it appears, then it adds strong evidence to support the vaporized silicon hypothesis. But the model doesn't account for certain behaviors described in ball lightning encounters, such as the ability to pass through solid matter. So what does this mean? Well, either those accounts are wrong, or ball lightning could actually be a collection of separate phenomena. In addition to proposing theoretical models, scientists have attempted to reproduce ball lightning in laboratories with incredible results. One experiment at the Max Planck Institute reported producing a ball lightning type effect when researchers discharged a high voltage capacitor into liquid water. In 2006, researchers at Tel Aviv University conducted an experiment by pointing a microwave drill made up of a magnetron and a microwave beam at a strip of solid silicon. When the researchers pulled the beam away, the drag produced a tiny ball of plasma, nearly identical in appearance to reports of ball lightning. An astonishing result, to be sure, but is this laboratory-produced phenomenon the same as the ones reported in nature? It's very possible, but as of right now, we simply don't know. Another experiment, conducted in 2018, came to even more stunning conclusions. Using advanced experimental engineering, physicists successfully created a Shankar skyrimion, a quasi-particle that is like a tangled three-dimensional magnetic field. Without getting too complicated, what the researchers did was apply an external magnetic field to a system of rubidium atoms near absolute zero. The magnetic field controlled the atoms in such a way that they all spun facing the same direction on the knot surface, while twisting unusually on the inside. In other words, the magnetic field maintained a stable spherical configuration, able to do things like squish or deform while still retaining its essential properties. This discovery could have major implications for quantum computing, but researchers also believe the synthetic magnetic field they created models the expected electromagnetic field of ball lightning. This theory will require a lot of follow-up research, but it's a promising discovery that could explain some of ball lightning's alleged characteristics, such as the ability to pass through solid barriers. So there we have it, a survey of the incredible history of ball lightning encounters, as well as the cutting-edge research that has come tantalizingly close to proving it. So what do you think? Do you find any of these theories convincing? Have you, or anyone you know, ever experienced an encounter with something that looked like ball lightning? I'd love to hear about it in the comments. All the best, and see you next time. Thanks for watching. Making this video required some long-term planning and work, which we were only able to do thanks to the consistency and sustainability of your memberships as Astronauts on Patreon. A huge thank you to everyone who has signed up, and if you'd like us to make more videos like this, you can join with the link down below. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.